Okay, let's dive right into this explainer by recognizing a pretty profound truth about our modern world. The most invisible forces are very often the ones driving the biggest global markets. I mean, when we think about massive geopolitical power, our minds usually go straight to oil, gas, or maybe silicon chips, right? But today, we're going to look at something much more fundamental, something that literally enables the entire clean energy revolution. We are looking at the humble, yet absolutely incredibly powerful permanent magnet.
I absolutely love this quote from our source material. If you were to pick one thing to magically erase from existence that would bring all of modern life to a screeching halt, your best option would probably be magnets. Seriously, think about that for a second. If you take apart your cell phone right now, you'll find a whole bunch of them. They're in the speaker, the microphone, even stabilizing the camera lens. They are the hidden backbone of our hard drives, our everyday electronics, and crucially, they are the absolute core of the clean energy transition.
So treat this explainer as your macroeconomic investment briefing. We're going to cover 5 key areas today, starting with the hidden $38 billion market. Then we'll look at the rare earths monopoly, how iron nitride is disrupting EVs, fusion's trillion-dollar moonshot, and finally, we'll track exactly where future clean energy investments are flowing.
Let's start with Section 1, the hidden $38 billion market, the very foundation of clean energy.
Get this, in 2023 alone, about $38 billion worth of these magnetic materials were produced globally. And without them, clean energy simply does not work. To understand why, let's just compare 2 huge applications. In an electric vehicle motor, electricity flows into a shaft, creating a magnetic field. When you add permanent magnets, their fields actually push against that central field, making the shaft rotate and the car drive forward. Essentially, they turn electricity into motion. Now think about a wind turbine. It is the exact same concept, just running in reverse. The wind moves the blades, which causes a magnet to spin around a wire, and boom, it creates an electric current. It turns motion into electricity. It's elegantly simple, but it's utterly foundational to our future.
Which brings us to Section 2, the rare earth monopoly, and some massive supply chain vulnerabilities. Now here's where the story pivots from cool engineering to some really high-stakes geopolitics. Currently, 92% of the global rare earth magnet supply is concentrated in just one country, China. Most permanent magnets today rely on rare earth metals, typically neodymium. And it's not that these trace elements are only buried in Chinese soil, not at all. It's that over the years, through some incredibly deep government and private investment, China has built this remarkably cheap, concentrated supply chain that spans all the way from raw mining to the final finished product. To truly grasp how fragile this makes the rest of the world, we have to look back at an incident from 2010. It started small. A Chinese fishing vessel was captured by the Japanese Coast Guard. When Japan refused to release the crew, reports indicate China allegedly threatened to cut off its supply of rare earth metals to Japan's massive electronics industry. And the result? Absolute market firestorm. Rare earth prices skyrocketed pretty much overnight. This incident was a massive wake-up call, proving how quickly concentrated supply chains can instantly turn into devastating market panic and severe material security risks.
So we're left with a stark contrast in how this plays out today. On one hand, China's incredibly streamlined supply chain has allowed EV makers in places like Shanghai to aggressively manage costs and achieve global EV dominance. I mean, more than half the vehicles sold in Shanghai in 2024 were electric. On the other hand, Europe is trying to fight back by exploring this massive deposit of rare earths in Norway. But starting a new mine from scratch, that is an extreme uphill battle. You have complex permitting, massive environmental concerns, and the need for staggering capital. Just the first phase in Norway is going to cost around 1 billion euros and take more than a decade to actually produce at scale.
Moving on to Section 3, iron nitride disrupts EVs, how we might bypass rare earths entirely.
What if we didn't have to wait a whole decade and spend billions digging a giant new mine? What if this massive geopolitical headache had a pure science solution? Well, iron plus nitrogen equals no rare earths required. Professor Jianping Wang at the University of Minnesota literally spent 20 years trying to find a stable molecular structure that combines 2 of the Earth's most incredibly abundant elements. And by doing this, innovators are essentially engineering a potential billion-dollar business that bypasses those geopolitical bottlenecks completely.
And this breakthrough translates into a super scalable 3-step lab process developed by a company called Niron Magnetics. Step 1, you start by making highly engineered iron oxide rust nanoparticles. Yep, rust. Step 2, you process that non-magnetic rust further into iron nitride, which dramatically cranks up its magnetism.
And finally, step 3, you make that powder highly alignable so it forms these tiny chains, and you compact it into a finished magnet. It completely demystifies the science and avoids the staggering environmental and financial costs of traditional mining.
And let me tell you, the market is paying very close attention to nitride. They have secured over $100 million in total venture capital. Even more telling, over $30 million of that is coming directly from legacy automakers like GM and Stellantis. These auto giants are heavily investing to secure their EV supply chains, aiming to actually integrate iron nitride magnets into their vehicle lines in just 3 to 5 years. Though, funnily enough, nitride's initial product launch is actually focused on audio speakers and electric guitar pickups, so this revolutionary clean energy tech is basically going to be tested by local rock bands before it ever hits the highway.
Now, to be totally transparent about the science here, we do have to talk about something called coercivity. Basically, this is a magnetic material's resistance to demagnetization when it gets exposed to other magnetic fields. And right now, this is the main drawback of iron nitride. See, while it works flawlessly in static applications like a speaker or a guitar, an electric vehicle motor spins incredibly fast, exposing the magnet to intense demagnetizing fields. Fixing this coercivity issue requires a bit more fundamental research, which is exactly what all that VC funding is paying for.
All right, Section 4, Fusion's trillion-dollar moonshot, the ultimate energy play.
So we're leveling up from the billion-dollar EV market to literally trying to replicate the power of the sun. This is no longer just about moving cars, this is about trying to hold a star inside a machine. To do this on Earth, you need a tokamak reactor, and to make that work, you absolutely need a superconductor. A superconductor is a material that has zero electrical resistance, meaning it can carry current without generating any heat whatsoever. This solves a massive engineering hurdle. Older reactors used copper magnets, but copper resists electricity, meaning energy gets lost as heat. You end up having to pump more electricity into the magnets than the fusion reaction actually creates, which obviously leaves you in the red. Superconductors fix all of that.
But not all superconductors are created equal. Low-temperature superconductors require conditions close to absolute zero, and because magnets hate being that cold, their magnetic field is limited, meaning you have to build the reactors absolutely massive. That is exactly why the ITER project in France is projected to cost up to $65 billion. But contrast that with high-temperature superconductors, or HTS. This is a Nobel Prize-winning material that comes in literally a thin tape. It allows startups to make magnets that are 10 times smaller, wildly cheaper, and significantly faster to commercialize.
I really want to hammer home just how powerful this HTS tape is. Consider this number, 35,000 amps. A startup called Commonwealth Fusion Systems is building these new magnets, and in their testing chambers, they pump up to 35,000 amps of current into them. To put that into perspective for you, you charge your cell phone at night with just one single amp. They're pumping the equivalent of 35,000 cell phone chargers into a single, compact magnet that is capable of lifting an aircraft carrier. The scale of this is truly mind-blown. Which brings us to our final part, Section 5, Future Clean Energy Investments, and where exactly the capital is flowing.
We've looked at the science, but let's follow the money and analyze the macro trends driving these technologies, from university lab experiments straight into commercial realities. For decades, fusion was largely just a government science experiment with minimal private backing, sitting around $500 million total. But if you look at just the last 2 decades, private industry has gotten deadly serious. We have seen a massive influx of roughly $7.5 billion pouring into about a dozen fusion startups globally.
And a massive player driving this momentum is Breakthrough Energy Ventures. That's the VC firm founded by Bill Gates specifically to fund early-stage clean energy. They are incredibly bullish on this, having invested in 7 different nuclear fusion companies. They initially backed Commonwealth Fusion Systems with $100 million and then helped push Commonwealth's Series B funding to nearly $2 billion. Heavy hitters like this are outright rejecting the old joke that fusion is always 20 years away. In fact, Commonwealth is aggressively planning to complete a commercial demonstration plant by the early 2030s.
But, as smart investors and learners, we've got to balance the hype with reality. And that brings us to the net power challenge, producing more power than the reactor actually consumes. This is the ultimate crucible for the technology. While magnetic confinement fusion has worked in lab settings a few times, it has never been consistently proven in a commercial-scale plant. Even if these incredible new HTS magnets tip the scales in our favor, building a full-scale fusion industry that can reliably power cities, that is still likely decades away.
So as we review everything we've talked about today,
The absolute most important takeaway is that magnets aren't just those boring static things stuck to your fridge anymore. Scientists are literally in there manipulating their molecular structure, whether it's combining iron and nitrogen to bypass Chinese rare earth monopolies, or using superconducting tape to contain the heat of a star. Magnets are following the exact same rapid evolutionary trajectory we saw with computer chips and lithium-ion batteries. And for sure, they are poised to unlock massive, entirely new sectors of the global economy.
Which leaves us with this final, really vital question. Will mastering the invisible force of magnetism be the ultimate key to breaking supply chain monopolies and actually unlocking a true clean energy future? It is absolutely fascinating to think that our geopolitical security and really the future temperature of our planet might rely completely on these invisible forces. Thank you so much for joining me for this explainer. Keep asking those big questions, and we'll see you next time.